My name is Chelsea Troy. As mentioned, I am a staff software engineer at Mozilla on a team called Pocket. I teach a couple of courses at the University of Chicago in their master's program in computer science. And I blog at chelseatroy.com. You can see the URL right there. I'm also on Twitter at Hey Chelsea Troy, and you can see the handle right there. And today we're going to be talking about what counts as a programming language. Now, I have to confess this is a little bit of a sneaky title because this is a talk ultimately about something called assumed context. And that's what we're going to start with in this talk. Now, assumed context is a broader topic than programming languages specifically, and it applies in a lot of areas that aren't specifically what counts as a programming language. But we need to understand assumed context in order to address the question of what counts as a programming language. And so we'll be discussing that at the beginning of this talk. But before we do that, I want to start this talk the way that you would expect a talk entitled What Counts as a Programming Language to start. And I'm going to do that by introducing some prior art. So before I wrote this talk, I went on a search engine and searched for the question, what counts as a programming language, to see what sorts of results I would get. And in particular, here are two of the most inclusive examples that I saw on the internet of explanations for this question. So Code Academy describes a programming language as the tools we use to write instructions for computers to follow. And Wikipedia similarly describes a programming language as a formal language comprising a set of instructions that produce various kinds of output. Now, these both sound like relatively inclusive definitions. The second one in particular, a formal language comprising a set of instructions that could apply to a variety of different things. It could apply even to potentially some natural languages in which commands are given. But these two definitions differ pretty considerably from what comes up when you walk into an office or into a conference and you ask software engineers what counts as a programming language. So in having this conversation, I've had a number of different questions come up. Does it have to be Turing complete to be a programming language, for example? Now, in practice, this typically connotes whether you can assign variables, have branched logic, looping, those kinds of things. And this is a question that often comes up on whether or not something is a programming language. Is it Turing complete? Another one is, does it have to be usable for solving a specific kind of problem? That is a programming language just anything that a programmer uses to do their job? Are we defining it in the practical terms like that? And by that definition, does that mean that everything that I use is a programming language just because I'm a programmer and I'm using it? How about this one? Does it have to actually be used for solving that specific kind of problem? A good example that I like to use here is a problem that we use to teach people programming languages, which is to write tic-tac-toe on the command line. So they'll use a programming language to write some sort of command line tic-tac-toe implementation. And we generally wouldn't argue that what they're using isn't a programming language. Maybe it's, Elixir or Python or Ruby that they're using. But we can also solve the tic-tac-toe problem with a little bit of conversation and 4 lines drawn with a pencil, right? Does that make the programming languages that we use to make a tic-tac-toe game any less of programming languages because we don't necessarily use them to solve the tic-tac-toe problem? And finally, does it have to have a compiler or an interpreter? Now, this one is the most interesting to me because it seems of the 4 often like the most technically rigorous one. But at its core, what a compiler generally does is it converts computer code from a front end, that is the syntax that we're writing, into something that, into machine code, into something that a machine could run. Or an interpreter would then run that, And so in a way, we have this compiler and this interpreter stricture that says what you need to be doing is you need to be converting your front-end programming language into bytecode that can run on a virtual machine, or into machine code that can run on a specific machine. At its core, though, that requirement is a type of translation. Now, we have compilers that might do that compilation in full. We also have transpilers that might convert one programming language front end into, for example, another programming language front end, or into the bytecode that's used for that front end, the way that Kotlin compiles down to the JVM, which was originally designed for Java. At what point do we draw the boundary on what kind of translation counts as compilation? Is it at the point where we're using specifically machine code or virtual machine? Or do we count in that compilation process the translation of CSV to JSON, or JSON to CSV, or one natural language to another? And so this is an area where, without those specific boundaries, this may really be the most inclusive of all of these strictures. Now, as you'll learn, I don't think necessarily these strictures are as useful to us as we might assume that they are when we're having this conversation. So I want to move to some specific questions that might give us a better handle on how we decide whether something is a programming language. Now, another question that sometimes comes up is whether a markup language is a programming language. And this one, I would say that there is a little bit less debate around than some of the others. I think in a lot of the conversations that I've had anyway, it's generally accepted that a markup language doesn't count as a programming language. We don't count things like HTML or Markdown or XML or JSON. These are data representation formats, and they don't necessarily implement any kind of logic in there, right? We aren't specifically using these for branch logic and those kinds of things. They aren't what we would say Turing complete. They don't pass that Turing complete test. Now, this one is not debatable at all, and some of the ones are more debatable. And I want to stop here and note that it is rather interesting that the way we tend to define what counts as a programming language often falls along the lines of which things are largely done by the dominant demographic in tech and which ones are largely done by the marginalized demographics in tech. We see a trend of folks viewing sometimes, for example, front-end programming as a less technical topic than back-end programming, which falls largely along the lines of the demographics of who tends to be a front-end programmer versus who tends to be a back-end programmer. And going back in history into the 80s and the 70s, when computing wasn't considered such a technical task, was precisely the time that women were largely the ones completing computing tasks. And as it became a more largely male profession, it also became largely a more regarded as technical profession. So I don't want to lose sight of that as we're talking about what counts as a programming language. We'll come back to that. Here's an area where there's a little bit more debate. Is a query language a programming language? So SQL, for example, that's a declarative protocol that we use for fetching data out of a relational database. Cypher is a query language that we use for getting data out of a graph database. Now, we'll talk a little bit more about Cypher later. But when we talk about whether a query language is a programming language, I find that there tends to be more disagreement than when we're talking about whether a markup language is a programming language. So maybe it's time to take a step back and think about what it is we're trying to describe when we describe a programming language. We said programming languages, but maybe some context is missing here. Now, let's talk about what context means. A context is a descriptor that characterizes your specific situation. The state that I grew up in is a context. The cultures of my parents is a context. The country I grew up in is a context. The language that I spoke as I was growing up is also a context. Those contexts shape our experiences of the world. So I'll give you an example. In English, we have a word for red and we have a word for pink. Pink is a tint of red, red mixed with white. And when we look at pink or red, we have a very specific idea of which of them is which. Telling the difference between pink and red is something that we think of as two different colors. Now, that's not the case with blue. There are dark blue, various shades of blue, and then light blue. But I don't know whether I would say that this pen is dark blue or light blue. That would be an easier distinction to make if my first language were Russian, because Russian has a number of different words for different shades of blue. Literally, the way that I see color is different than the way that somebody with a different first language sees color. This is the best example that I can think of to microcosmically demonstrate that the things that inform our context also shape our perspective, the way that we see the world. And it's really important for us to be aware of that context, because when we are unaware of the context that we're in, we can accidentally mistake our specific case with an imaginary general case. We can conflate what we perceive to be true with what is actually true. We can conflate the way we view things with the way things are, not realizing that others might see them from a completely different angle. Now, before we return to programming languages, let's look at another example of a context-specific idea to make this clear. There's a phrase on this slide that I'd like you to read. Generally, it is better to optimize our code for legibility than for speed. Can I see a show of hands in the crowd who agrees with this? Do you agree? Generally, it's better to optimize our code for legibility than for speed. All right, I see a few hands up. Maybe a little fewer than normal. That's interesting. I'll talk about why that is. So, the vast majority of my career has been spent writing end-user applications. And recently, I wrote my first interpreter for a programming language. I was following Bob Nystrom's Crafting Interpreters project online. And one of the first things that happens is there is this very large case statement that you use to determine which tokens are in the programming language that you are reading. And I thought, well, that seems a little bit messy. That doesn't indicate the hierarchy of these different tokens. And so I rewrote it with some nested if-else conditions. And then I reached out to Bob and I asked, why is it written with a giant case statement when it could be written like this? And it's so much clearer to understand which tokens are being used and why. And he responded to me and he said, yes, that is clearer for a new developer to understand. But the thing is, it's slower. Those conditionals run more slowly, and they have to run one after the other. A nested conditional is blocked on the original conditional, and so that code is going to take a lot longer to run than the case statement. In an end-user application, I have the luxury of thinking about legibility more than speed in general, because my programming language is fast enough that looping over 14 keys and values is going to happen instantly from a human perspective, regardless of how I do it. But the reason that that's the case, the reason I have that luxury, is that the people who wrote the programming language optimized for speed rather than legibility. I get to optimize for legibility in my end-user application because the programming language designers optimized for speed. A really wonderful example of this is in the CPython interpreter, which is open source, and you can take a look at it. The heart of the CPython interpreter is a 1,500-line case statement. And if that is too big for a computer to load, what it does is it splits it in two for you, into two case statements. You can go and look at the actual code. It's really amazing, but it really gives you an appreciation, gave me an appreciation for the way that solving different problems changes whether this thing that's generally true is true or not. Let's look at another one. Generally, composition is preferable to inheritance. Do you agree with this? Is composition generally preferable to inheritance? This is one that I've talked about with a few Elixir devs. It's one that we talk about among Ruby developers as well. And in general, again, when we're talking about this, we're talking about end user applications, an application that's built on a framework like Rails or Android or iOS, right? We'd rather compose things together than inherit from classes. In functional programming as well, we'd rather compose functions together. Here's the thing. We're writing an end user application in a framework where we're inheriting from things. In iOS, you inherit from a view controller. In Android, you inherit from an activity. In Rails, you inherit from a controller as well. Now, the reason for this is that behind the scenes, those objects need to take care of a lot of different things. In particular, for example, with the mobile frameworks, we are talking about an application that needs to fit on a device the size of my palm. There just doesn't happen to be that much memory available. And so object conservation is extremely important. And framework developers have two options. One of those options is make the end user application developers worry about object conservation. That's going to make developing those applications harder, and inevitably end users are not going to do it right, or rather end user application developers are not going to do it right. So instead, what happens is the framework handles a lot of the object conservation steps for you in superclasses that you then inherit from to write an end user app. Again, we have the luxury of preferring composition to inheritance in an end user application because the framework designers have used inheritance to abstract some of the gory details away from us. This is true in a specific context and not in others. So now we have to talk about what generally means. We said generally in both of these cases. And what did it mean? It meant in most cases. But which cases are those most cases? When we teach beginner programmers, we use generally because we want them to have a place to start. We don't want to overcomplicate things for them as they're just starting out. And I think that's the right choice. But I also think that by the time we've reached the point where we are teaching those programmers, where we are using the phrase generally to teach somebody else, it's incumbent on us to understand what we mean by generally. When we say to someone, do this in most cases, it's important for us to know which cases are most cases and when this rule no longer applies. Let's look at another use of the word generally. Elixir, Ruby, Python, JavaScript, a number of other programming languages are generally considered to be considered, watch that, are considered to be general programming languages. Erlang is considered general too, maybe a little less so because it's a little more back-end specific, right? Now that we know to think about this term generally, we find ourselves needing to do it again here. When we say that something is a general programming language, what do we mean by that? Maybe a way to figure that out would be to contrast general programming languages from what we consider to be domain-specific programming languages. Cypher, domain-specific language for fetching information out of a graph database. RSpec, domain-specific language for unit testing Ruby applications. Regexes, domain-specific language for munging, potentially, text inputs. By the way, if you're more interested in regexes, there is a really great talk by Betsy Habel about regexes and about why those are designed the way that they are. Now, we have this word general, and we're contrasting that with domain-specific. But here's the thing. What if the general case is in fact specific to a domain, and we only think it's general instead of domain-specific because we consider its domain to be the default one? What if general programming languages are in fact domain-specific programming languages, but they're specific to the domain that we're using in most cases? Much in the way that, for example, we have this idea of a unisex t-shirt. but there isn't really such thing as a unisex t-shirt. There's a men's cut t-shirt, which is what we're referring to when we say unisex t-shirt, and there's women's cut t-shirts, which are considered a special case, even though women are half of the world population. So what might that specific case be for general programming languages? I might argue that the default domain for programming languages might be end-user applications where the user can change something. We're not talking about static websites because, as we've established, markup languages that make up static websites are generally considered to be not programming languages. But when we are building an app where there are inputs and forms and connections to databases, that's the sort of problem that we find ourselves solving with quote-unquote general programming languages. Now, maybe this really isn't some kind of default domain. Maybe it's just the one that has received the most attention. We can talk about why that might be in the questions later if you like, but I'll skip over that for now to talk about some other domains where we use programming languages. Now, what I'm showing you here is some example code in Alloy. Alloy is a domain model verification tool that we use when we are developing a large or potentially complex domain that we need to write some software for. We use it to verify our assumptions about the way that that domain is going to work. Here, I'm using Alloy to verify the rules around the way a pipeline is going to be built. I want to make sure that there isn't any way to have my stages become circular. I want there to be a beginning and an end, and I want there to be a linear process through the stages from beginning to end. Now, you wouldn't use Alloy to write an end-user application. You would use Alloy to ensure that you understand your domain model before you write that application. In general, end-user application developers aren't using something like Alloy, or they aren't using, there's another one called TLA Plus that we use for formal verification. Instead, the solution that we have alighted on in end-user application development is to go ahead and start writing code, get 6 months down the line, have a 60,000 line application, and at that point, discover that there's some kind of complex bug where we can get 17 steps into our process and have corrupted the state of the program somehow. And at that point, we have to go digging through the program to figure out why that happened, how it happened, when it happens, how to fix it. It's tough, and we haven't necessarily figured it out. So what we do is we make a bug in Trello or Jira or Pivotal Tracker. We put a bunch of angry faces in the ticket. And then we come back to it every 6 months and make another half-hearted attempt to get it fixed. We never do. That's certainly not the ideal approach. I wouldn't even call it a better approach. So now the question is, what can we learn as programming language designers and users from something like Alloy or TLA Plus that's used in a different domain but solves a problem that we find ourselves devoting a lot of resources to failing to solve on a regular basis? Let's look at another example, Modelica. Modelica and another similar language, Simulex, are largely used for modeling relatively complex physical processes. So this is used, for example, at Ford General Motors for modeling the pieces of cars to figure out how they're going to work together. Now, we have relatively complex processes that we attempt to model in general programming languages as well. And once again, I find myself with a question. What could we learn from languages like Modelica and Simulex that make it their business to solve complex problems with moving parts where the different pieces affect each other in a relatively streamlined way? There may be kernels of knowledge in there that would make the modeling of complex logic less difficult in what we consider to be general programming languages. Finally, let's talk about Cypher. Now, Cypher has come up a number of times in this talk, and the reason for that is that I just love it. It is a database query language, and I think one of my favorite things about it is the way that the syntax draws a little picture for you of exactly what it is that you're trying to do. You've got these nice round parentheses that create a sort of an elliptical structure around your objects that you're trying to get out of the database. And then you have the square brackets, which indicate the kinds of relationships that you're trying to find between those objects. I like Cypher because in a way that I haven't found with SQL, it provides me with a diagram of what it is I'm trying to do. Now, I know that I have not been a programmer as long as many of you have been, but in my time, at least so far, I've seen 3, maybe 4 attempts to provide a diagrammatic representation of a general programming language. And all of them have failed in one way or another. So I find myself wondering, what can we as users and designers of programming languages learn from a domain-specific language like Cypher that makes its business a syntax that diagrams the queries we're trying to make? There are other domains in which folks are regularly using code to solve problems that are different from the ones that we have to solve, but have similar threads. For that reason, I argue that paying attention to those other domains outside of our domain can make us better at this programming thing. I find myself wondering what we can learn as engineers from process modeling, from simulating physical systems the way that we do in Modelica or Simulex, from fetching network data the way that we do with Cypher. Now we come back to a question that we talked about at the beginning. What separates converting CSVs into JSON format from parsing a high-level programming language into an abstract syntax tree? Of course there are differences, but I think it's very important to articulate those differences and understand exactly what we're talking about. How the things that we do differ from the things that others do, and where there might be parallels where we can learn from each other. I think there is more value in learning to identify contexts and share information across contexts than in formalizing our understanding of the difference between domain-specific languages in 2 separate domains. Because I think the subtext of defining what is or isn't a programming language often comes with a normative judgment of what is technical and what is not. And when we are describing a general programming language, we tend to think of that as the most technical thing. And we tend to make the mistake of thinking that the more technical thing has nothing to learn from the less technical thing. And in so doing, we deny ourselves the opportunity to reach across domains and learn more from others who are solving similar but different problems to ours. Computer science is an extremely young field, tops 150 years old. We have a lot to learn, and we can benefit. In fact, I'd argue it's imperative that we learn from the different domains in which programming languages are being used. Otherwise, we run the risk of replicating lessons and failures that other domains have already experienced and can warn us about. Here's the point. You and I swim in a sea of context. And unless we make an effort to specifically identify that context and understand that the things we think of as true might not necessarily be true for everyone else, and why, we get a lot of benefit from that position, And it's important for us to practice that skill. So I think we can access a deeper and better connected understanding of programming languages, and maybe anything, but I'll stick to what I know, by learning to find the invisible context hidden in general statements. So how do we do that? I have some thoughts on how we do that, but I'm going to provide a process here that hopefully will help folks practice. First, I'd like folks to ask themselves, what principles, ideas, or best practices do you think of as always right or generally right? You don't need many, just 2 or 3. I recommend pulling out a notebook and writing them down. What best practices do you think of as always right or generally right? Second, maybe there is a context in which that is the case. I recommend specifically looking for it, looking for the water around you. So for example, if I had written down composition is preferable to inheritance, that would be one of my best practices. Now I'm looking for the context for that. Where is that true? Who tends to use inheritance rather than composition? And why? Next, go looking for contexts that are different from yours to better understand what your best practice is, why your best practices work in your context. So we talked about the example of this. I'm looking for folks who tend to use inheritance over composition, and I'm trying to understand why. There's a side benefit to this, which is that nothing demonstrates why something works better than an example of where it doesn't work, because it gives you helpful information about why this approach solves your problem so seamlessly and where you might encounter seams if you try to blanket apply this best practice everywhere. Finally, go looking for contexts that are similar to yours. What can your tried and true approaches contribute to this similar context? Perhaps in that context, your best practice, my best practice of composition over inheritance or something, might be valuable to others who are solving a similar problem. And also, what can you learn from the similar context about what to try in your own context? What lessons can I draw from another domain to be better at working in mine? I think that developing this cross-contextual understanding of our craft opens a lot of doors for us to understanding the way other technologists think, and in so doing, refine the way that we think. Maybe I can learn to identify different shades of blue just as quickly and as confidently as I identify the difference between red and pink. And once I've done that, I have a much broader and more specific spectral angle with which to view the world that I live and work in. And that can only make me better at what I do. So with that, I'd love to open the floor to questions. Are we doing questions?
Absolutely, and we had one in the app. Please post questions in the app, and we'll take them from there. So we have one question from, okay, it's jumping up and down. So from, let's start with Don Barlow. Don, if you're there, can you unmute yourself and ask?
Hey, Don.
Yeah, hello, I'm good. Thank you very much. Excellent presentation. Yeah, you mentioned like the design of regex parsing libraries talk. What was that? What was her name? I didn't catch that.
Absolutely. Her name is Betsy, B-E-T-S-Y, Haibel, H-A-I-B-E-L. She also recently introduced me to a paper by Peter Nauer called Programming as Theory Building, which if you're interested in the regex talk, you might also really like that paper. I got a lot out of it. It's about the way that having an understanding of sort of the theoretical underpinnings of the problem you're trying to model as a software engineer is really helpful to implementing the right solution, which when I summarize it like that, sounds very trite, but a lot of the details in that paper were really helpful for understanding that idea and thinking about how to do it.
Excellent, thank you.
Yeah, absolutely.
Great, thanks. So we've got a question from Ayush Pandey. If you're there, if you can unmute yourself.
Hi, Ayush.
Am I audible? Hello. It was a very wonderful talk. I really got a very different perspective. My question is, in the beginning of the talk, you mentioned that markup languages tend to generally not be used for programming. I have sort of a different approach to this because I'm using YAML to execute certain tasks in it's basically a framework that a few of us in the university are building, and the way that the programmers for that framework specifies the tasks is through YAML. So I don't know what your opinion on this is. We had quite a nice discussion in the chat where we concurred on thinking that it generally ends up being a domain-specific language, which we sort of molded into our own use case.
Yeah, that's an interesting point. So YAML is an interesting case. Just for folks in the crowd who haven't used YAML, YAML is often used for configuration, so it is generally used in configuration files. But we might think of it as sort of data and configuration storage is usually the way that it's used, and it is whitespace specific, much in the way that Python uses whitespace to demarcate structure, whereas Ruby uses syntax to demarcate structure. YAML uses whitespace to demarcate structure, much in the way that JSON uses curly braces and colons to demarcate structure. And I think that this illustrates where sort of the lines blur. I think that your example case there illustrates the circumstance where perhaps the distinctions between these different things and what counts as a programming language versus what doesn't count as a programming language is not as important as what strengths each of them bring, what problems each of them might be well positioned to solve, and how we might end up using the appropriate tool for the job. I was talking to Hilla Wayne a little bit about this a couple of weeks back, and about whether maybe there isn't a problem with saying what's a programming language and what isn't a programming language. The normative judgment around what's a programming language and what isn't a programming language, and therefore what's technical and worth doing and valuable, maybe that's not so great, but maybe distinguishing what's a programming language from what isn't is valuable in the sense that it gives us an idea of what problems a tool might be used to solve. And I've thought about that a lot. I think programming language versus not programming language at this point is too overloaded and normatively judged to use for that. So I think in a theoretical case, it might be useful for that. I think in the case of our actual world, we would have to come up with different distinctions. Maybe that would be naming our domains rather than thinking of things as general versus domain specific. But I think that your YAML use case provides a good example of where differentiating those different domains and trying out different tools might sort of prove the point of the value in thinking about these tools in terms of the problems they solve and where there might be cross-cutting lessons.
Okay, thank you for that. We've got one more question. Well, we've got a few more questions. If you have any questions, please post them in the Q&A section. They're coming in. So we've got a question from Mr. Robert Birding himself. Hello, Robert.
Hello,
sorry,
hello Francesco. Yes, is my mic working? Sorry, yeah. Good.
Working, yes. System working seems to.
This was just a bit more philosophical thing, really. But what are different domains? How can you tell domains are actually different? I mean, they might be called, what I was thinking, they might be called different things, and the things inside them might be different names and stuff like this. But when you start looking at them, they're actually the same, right? That's just sort of a more philosophical point for it. So you might say, okay, I'm looking at this domain, and then I'll go look at another domain, and I might realize they're actually the same thing. Like your fishes, they might swim on one side of the tank and go to the other side of the tank and think, oh, I'm somewhere completely different now, but I'm not, right? That's just, I don't know, it's just, I don't really expect, I don't have an answer really a question, but just a thought. But, yeah.
It's an interesting one, and identifying that two domains that were previously sort of considered as different may in fact be the same, I think is a potentially valuable source of cross-cutting insight, where if we have two domains that different folks have been working on and they've come to different solutions, there could be a lot of context sharing there that would end up allowing both domains to advance. And I think there might be a question here, and how do you go about finding those domains that might be considered different from yours, but are in fact the same? And the only answer that I have come up with, and I don't think this is a good one or a complete one, is to take the opportunity to ask questions of people who solve very different problems and try to understand how they're solving those different problems and why those problems are different from the ones that we solve. And I think that might be the way to find those similarities.
Okay, yeah, no, just sort of thinking aloud more than anything else. Okay, thanks, yes.
Brilliant, thanks for that. So Tracy Onim, you had a question, and Brandon maybe also had a comment following the question. So Tracy, over to you.
Hi, Tracy.
Hi, hello. So I've been used to use two query languages, that is Postgres and SQL in Elixir. And Elixir has a way of accommodating those two languages. So I was wondering if it's the same for Cypher.
If it's the same for Cypher, that is a good question.
Does
anybody know if Elixir has tooling for working with graph databases?
Brandon, yeah, you had the answer there, if you're there.
Yeah, so at least Neo4j specifically, which uses Cypher, it has like a language agnostic protocol called Bolt. So I posted a link to the Elixir implementation of that, where you can directly write Cypher queries and send them with Elixir.
Thank you.
Cypher's awesome. Highly recommend a look if you're interested in, but obviously I'm biased. So.
Okay, I think we've got two more questions. Zaki, you had a question?
Can you guys hear me?
Right.
So my question is around first principles approach, right? So I think about first principles about programming. My programming is all about, for me, manipulating data, right? How do I get that data? How do I get that picture uploaded, right? It's data back and forth. But in a way, coding is also kind of like writing, right? And you want to make what you're writing as clear as possible. And so I'm just trying to think about your approach about the fishbowl, right? Which is, I think, taken from a very small book, right? My sister got it for me, and it was very interesting. So how does first principles align with this process you've given us on deciphering context?
Mm-hmm. Yeah, this is an excellent question. I think that first principles, we generally, learn these first principles as we're starting to program. And I think that that is an excellent place to start in deciphering context. We can take a look at the first principles. And I think the question there is, if these first principles are useful in the majority of cases we've seen, in what cases are they not useful? In what cases do I have to break them? In what cases am I forced not to use this approach? Or would I lean away from this approach, whereas normally I would lean into it? And I think that those cases are worth a little bit of study. And I think that it's worthy of that study for two reasons. The first one is that understanding those cases can broaden our understanding to alternative approaches and where those approaches might be appropriate. And the second thing that it does is it strengthens our understanding of the first principles themselves. We can understand why this is useful when we understand the specific shape of the problems that it's designed to solve. I think, you know, as we start to understand the contours of the coastline of what we previously thought of as this like expansive borderless land of where this problem is useful, then, or where this solution is useful, then when we are asked to justify that approach, we can have an easier time saying, this problem has these contours, it has these borders. These contours and borders make sense for using an approach like this one. Whereas if it had these different contours and borders, maybe I would have done this other thing. And so we have the opportunity to compare it to an alternative and demonstrate it to be the better approach in a given case, rather than the answer, it's the best practice or it's the first principle, which helps other people to gain a better understanding as well of why it is that we've done something. In particular, I have found that junior engineers really appreciate being presented with a few alternatives and having it explained to them. This is the one we most often use because this is the shape of the problem it solves, and that matches the shape of most problems we find ourselves solving here.
Wonderful. Okay, let's try to squeeze in there a few more questions. I don't think we'll manage to get through them all, but Jonathan Arnett. By the way, if we don't have time, you know, hopefully, Chelsea, you'll then join the Toucan Lounge and people can come in and find you and ask you questions there as well, right after the break. So
absolutely. I'll also share my email and Twitter handle and everything.
Yeah, there's some really great questions which are coming. Jonathan, over to you. I think this will have to be the last question, unfortunately. There are also questions from Daniel Clegg and Lee Barney, but we can take them in the Toucan Lounge after the break. Yeah. So Jonathan, over to you, if you're there, if you could unmute yourself. No? Okay. Lee, do you want to go? Lee Barney? If you're there.
Sure, I'll go.
Yeah, go ahead, Lee. Hi.
Hi, Lee.
Hi. So the question is this. One of the most amazing experiences I have had as an engineer has been working for a company where we produced a solution that simulated semiconductor factories at a deep level. Mm-hmm. And to do that, I had to get out of my programming domain space, and I had to get into understanding the physicality of those factories and be in the production engineering domain space, get into their heads. Mm-hmm. I see a lot of people new to the industry who are very much into the code part, but not so much into that other domain. They seem to get stuck in coding domain instead of customer domain. So I'm wondering what we can do to assist those who are coming into the into this practice to be more aligned and open to these other domains.
That's a good question. I think it is easy when folks are just getting started with the programming. The programming feels unfamiliar and feels like the problem to sink their teeth into. And it can be tough, particularly if you feel like you're behind your peers and you need to catch up, to do what feels to you like slowing down and take a look at the domain and understand that domain and how you might model it. And so I wonder whether there are opportunities with folks who are learning to ask them how they would go about modeling their domains in code. And then maybe to have a conversation with them about how that domain might require that design to change. So an example of this that I often find is that I have my students complete a final project in each of their classes that they take with me. And they get to propose the final project, so it's something they're interested in, but they then have to meet a certain set of requirements with it. We come to an agreement on what it is that they need to do, how complex it needs to be. And I find that in doing that, they are more enthusiastic to understand the domain than they are with the homework problems that I assign them where I've come up with the domain. And that makes me think that a newer engineer feeling invested in the domain they're being asked to model might be an effective approach to teaching them the skills that they need to model it. Because the conversations that I have with them, I start to talk to them a little bit about, you know, do we want to keep this in an object? How do we want to store this? Can these things change? As people start using your system, what's going to have to change? What's going to have to scale? How are you going to make it easy for the future version of you to add the things that you need to add? And once I've asked them a couple of these leading questions, I find them brainstorming on their own, and they'll stop themselves and say, oh, we could do it like this. Oh, no, well, the way that the pool wagers that I'm modeling don't work that way. And so I would have to do it this other way. And I find that that enthusiasm for understanding the domain model starts to generate in those conversations more than in class itself. So I wonder whether that would be kind of the way to do that.